Hello, I'm Jeremy Gibbons, and I'm going to talk to you about how to design coprograms. So one of the problems that beginning programmers face is where to start. Where do my programs come from? I've got a programming problem to solve and a blank editor window in front of me and no guidance on where to get started. So one of the things we do is give them that guidance. We tell them to start by analysing the structure of the input you're going to consume. So for example, if you're writing a program to consume a list is either empty or it's not, so you'll have a case for empty lists and a case for non-empty lists. A non-empty list has a head X and a tail X's, and you're probably going to need those in the solution, so you already have some part of the structure of your output, of your program. More than that, lists are recursively structured. The tail of the list is another list, and so you can make a recursive call on that tail and use that in your solution too. So you get a more refined template for your program, where in the non-empty case you can use the head X, the tail X's, and the result of a recursive call on the tail H of X's. So this lesson, that program structure follows data structure, is a key lesson in introductory programming, and it's a central message of the very influential textbook, How to Design Programs. This book is built around a collection of design recipes, like the structural recursion that we've just seen, so let's look at those in a bit more detail. If you're writing a program that consumes some composite data, like a record, the advice is to name the components of that composite data. So here we're consuming a playing card. A playing card has a rank and a suit. We're probably going to need the rank and the suit in our solution, so let's start by naming them. R is the rank, S is the suit, and now we have to do something with R and S. Dually, if your input data is of a mixed data type, there are several variants. The advice, the design recipe, is to enumerate the alternatives. So here's a more refined model of a playing card. It's either a regular card as before with a rank and a suit, or it's a joker. And if we're consuming one of these cards, well, we enumerate the alternatives. It's either a regular card, in which case we do the regular card thing, which was the previous problem, or it's a joker, in which case we have to do something else. And then there's structural recursion. If your input data is inductively structured, like lists, the design recipe is to use structural recursion, as we saw earlier. So if you've got the problem of sorting to solve, and you hit it with the design recipe for structural recursion, you're led inexorably to a particular sorting algorithm, to insertion sort. So you consider the input, it's either empty or it's not. If it's empty, of course, you sort to get the empty list. Otherwise, it's non-empty with an X and an X's. You can make a recursive call on the tail X's. So now you've got the head X and the sorted tail. What are you going to do? Well, you have to insert the head into the right place in the sorted tail. So that gives you the main function. ISort xcons x's is insert x into ISort x's, and the only problem now is to define insert, which you can do by using the same techniques as on the subproblem. So this is all well and good. It's good advice for students. It helps them in designing programs, but it's only half the story. It's only half the story because it's only considering the input data structure, and the output data structure might be useful too. And I think it's missing a trick not to exploit that output structure and not to give the hint to students that they should do so. So let's look at those design recipes again, but from the other side, for looking at them from the perspective of output data structure. So now we're not consuming but producing a record. So here we're producing a date. A date has a day field, a month field, and a year field. So we're going to have to come up with a day and a month and a year. So let's name those. Let's have one subprogram per field, name those subprograms D, M and Y, and then we have to construct the record out of dm and y. Dually, if you have to produce variant data, enumerate the alternatives. So here's a safe division problem. You want to compute x divided by y, unless y is 0, in which case you have produced some separate value instead. So in Haskell, the idiomatic way to do that is with the maybe data type. Values of type maybe integer are either nothing or just an integer. And safe division, of course, if y is 0, it produces nothing, otherwise it produces just the quotient x divided by y. So what is the structure of this program? Where did that structure come from? If I couldn't immediately see the program, how can I make a first step towards it? So of course there is a case analysis, and there is a case analysis on the input, y. But it's not a case analysis determined by the structure of the input, because here y is not a structured argument. It's not a record, it's not a list, anything like that. Instead, it's a case analysis on the value of the input y. So this is not following our advice about considering input data structure. So that doesn't explain this program. Instead, of course, it's the output data structure that explains the program. The output data structure is a maybe, so it's either a nothing or a just, and the program structure has branches for the nothing case and the just case. So considering the output structure is a much better explanation of this program. And if you wanted to give a struggling student a hint based on structure, then it has to be the output structure you give the hint about. And then inductive data. So again, this is list, but now you're producing one, not consuming one. What are you going to do? Well, a list is either empty or it's not, so you have a case analysis. Under some circumstances you produce the empty list, and otherwise you produce a non-empty one. And if you produce a non-empty list, of course you have to produce its head x and its tail x's. But more than that, the tail is another list, so you could do that by making a recursive call. So a more refined pattern, which is often but not always applicable, something to consider, is the tail of the list x's is the result of a recursive call on some other input, of course generated somehow from Z. So your only question now is, what is the data that I should give to this recursive call? What is the seed from which I should grow the tail of the result? So if we go back to the sorting problem again, if you hit it instead with the structural co-recursion design recipe, you're led inexorably to a sorting algorithm, but not insertion sort, a different one, selection sort. So when does sorting produce the empty list? Of course, when the input is empty. If it produces a non-empty list, what is the head of the result? Well, that's the minimum of the input. And when it produces a non-empty list, the tail of the result is a result of a recursive call. From what data is that recursive call made? What is the seed from which we grow the tail of the sorted result? Well, that's the input data less the minimum element that you used for the head. So this is no more difficult, no more mysterious than insertion sort, as long as you realise that you can use the structure of the output data, another list, to determine the structure of your program. Now, how to design programs doesn't stop with structural recursion. It goes on to some more elaborate and sophisticated design recipes, and one of those is generative recursion. So this is a generalization of structural recursion. You make recursive calls on substructures, but the substructures are not immediately present in the problem. They're not obtained by projection from the input data, but by some more involved computation. You have to do some work to come up with the subproblems. So the design recipe for generative recursion says you've got a problem, you have a test for triviality. If it's trivial, you solve it by some other more basic means. Otherwise, you split it into subproblems, recursively solve those subproblems, and then combine those subresults into the overall result. Now, of course, this is a divide and conquer algorithm scheme, and students are being led by this design recipe to divide and conquer algorithms. But another way of looking at this pattern of computation is that it's about a structural recursion to grow a tree of subproblems, followed by a structural recursion to consume those results of those subproblems. So we start off with our initial problem, we break it down into smaller and smaller problems until we get to the leaves of a tree, which are trivial subproblems. We solve those, and then we can solve bigger and bigger subproblems until we get the overall solution. So it's a combination of the two patterns students will already have seen, structural recursion and structural co-recursion. The book is pretty apologetic about generative recursion. It describes it as an ad hoc activity, more ad hoc than the data-driven design of structurally recursive functions. Better to call it inventing an algorithm than designing one, because it requires insight, it requires a eureka step to figure out how to split the problem into subproblems. And then it goes on to say that we mere programmers can't be expected to come up with this kind of program. We have to leave that to cleverer mathematicians. But once they've had the idea, the insight, then we programmers can do the drudge work of implementing it. And I say that's too defeatist. I say that programmers can come up with this kind of solution. Now, I agree that it requires some insight, because the structure that determines the structure of the program is not there in your input data and it's not there in your output data. It's the structure in the middle instead. So yes, some insight, some eureka is required to come up with that. But from that point, there's no ad hocery. Everything is structured. There's a structured co-recursion followed by a structured recursion determined by your insight. So this actually reinforces the book's message that program structure follows data structure. The data structure in this case is something you have to invent. So that's my message. Program structure follows data structure. But we should not limit ourselves to considering input structure. We should consider the output structure too. If we have recursively structured data, that's likely to lead to recursively structured programs. But there might be structural recursion if they're over the input data, or structural co-recursion if they're over the output data. Once you've identified those two separate gadgets, structural recursion and structural co-recursion, you can put them together in new and interesting ways. And in particular, you can get divide and conquer algorithms by combining structural co-recursion and structural recursion. I've used Haskell as my vehicle for this talk, but none of this uses laziness. It all works perfectly well eagerly. Structural co-recursions will need some termination argument to demonstrate that they're producing finite data. But generative recursion in the book, How to Design Programs, needs this anyway. So this is not new material that needs to be covered in a course. It's already there. And of course, what I've said is not new. It's all there really in the work from the 1970s by Tony Hoare and Michael Jackson and Fred Brooks and many others. There's more discussion and there are more examples in my paper, How to Design Co-Programs, which is in Journal of Functional Programming. Thank you.